Okay, so this next video is about nuclear fusion. So the first thing is, what is fusion? And fusion is the joining, okay, now rather than saying joining, we would say fusing together of light elements into heavier elements. Okay, and this happens all the way up to iron. Okay, so like all our elements that are below iron, this is how all of them were formed. So we're going to look at the example of this. So we're going to use a common example that happens in nuclear fusion stars, and we're going to be looking at some of our isotopes of hydrogen. So I've got tritium here, so I've got hydrogen 3,1, and I've also got deuterium, so hydrogen 2,1. So we can also see that we've got our 1 proton, so my protons here being in blue and my neutrons here in red. Okay, so what happens is we want to fuse these two together. So we're going to bring them in, okay, and as they come together, okay, they're going to fuse together to make our helium atom. So again, our 2 protons and 2 neutrons. Okay, so they combine to make our helium nucleus, sorry, I should have said. And we also get an additional neutron. Okay, at that point, the fusing together also releases loads and loads of energy. So during that fusion, we get that production of energy in there. Okay, so we have the light elements forming together to make a heavier element. So we can see that it's heavier. We've got 2 protons and 2 neutrons. Okay, and we also have that additional neutron being left over here, but also giving us lots and lots of energy. Okay, so commonly this is actually taking place in stars. Okay, it's actually how stars are existing. It's actually going through nuclear fusion in its core, which is equaling out the gravitational force trying to pull it together, which is why stars are stable. So they're going through hydrogen into helium. Actually, in larger stars, so if we're going up to like kind of stars much bigger than our sun, going into kind of red giants and things, they can form into all the way up to iron elements can be formed in there. So if we're looking at those super red giants, they can form all the way up to iron, but that's just a little bit of extra information there. Now, nuclear fusion is really good because we're dealing with just like hydrogen, okay, and helium. I'm not dealing with any radioactive waste. This is like pretty amazing. I don't have to worry about the dangers. I don't have to worry about the safety of disposing it, but we haven't managed to harness this on Earth in a sustainable way. By that I mean in a way that is economical, is that we're getting enough energy out compared to the energy that we put in. So there's a lot of research and development going into this, okay? So you might think, oh, why is it so difficult? This sounds pretty easy. Well, you start thinking about the kind of composition of this. I've got 2 protons here. So 2 protons have positive charges, and I've got to get these positive charges so close together that they then fuse and stick together. But we know positives and positives, same charges, they are likely to repel. So we have electrostatic repulsion happening here. And what I need to have is I need to have enough pressure, okay, so enough force coming in to get these 2 close together so that they will join and fuse. So to have that high pressure, we need to have high temperatures, which is what is happening in the star. Okay, we have enough pressure from that core in the center, pulling it in and that high temperature. And that's why it's really difficult to recreate this on Earth, okay? Because we need to get enough pressure and temperature for it to overcome that repulsion between the 2 positive charges. So that's why it's a big field in science that's being having a lot of research done into it at the moment. So that's nuclear fusion, guys.